Hello everyone. I'm Abhishek Dahiya. First I would like to thank the organizing committee for giving me this opportunity to present our research work in this virtual event. I'm working as a research associate in the BEST group in School of Engineering at the University of Glasgow under the supervision of Professor Ravinder Dahiya. And today I would like to present our work done on zinc oxide nanostructures for flexible electronics. From now on, I'll turn off my video so it won't block the slides. Okay, so the present slide basically shows the motivation of our work. So as we know that high performance printed electronics, particularly made of inorganic nanostructures, is gaining a lot of interest for several emerging applications. For example, Internet of Things, mobile healthcare, smart cities, robotics, and so on, which basically require fast computation and communications. Low temperature printed assemblies of nanostructures has been demonstrated to fabricate micro nanosystems with different functionalities. For example, as you can see in the slide, nanowire-based piezoelectric nanogenerators, pressure sensor, electronic skin pressure sensors using nanostructures, and the photodetectors, chemical sensors, and so on. Among various inorganic material investigated for the development of high-performance printed electronics, zinc oxide nanostructure has shown potential because of its multifunctionalities. So this slide showing some of the appealing properties of these materials. So as a wide band gap semiconductor having 3.37 electron volt band gap, it has a high electron mobility of around 200 and high excitonic bending energy around 60 milli-electron volt, which find application in optoelectronics. It has also found application in energy harvesting because of its piezoelectric properties. Also, additionally, it has additional advantages such as it is a biocompatible material, it is abundant in supply, easy fabrication, and it has large number of nanostructures which can be printed to make nano devices. So various different integration approaches has been reported to assemble zinc oxide nanostructures over flexible substrates to fabricate printed devices. So these approaches can be classified as direct integration or as an indirect integration approaches. Indirect integration approach, low temperature growth process is used to grow zinc oxide nanostructures such as nanowires directly over flexible or stretchable substrates. Following that, further device manufacturing process are performed to finalize the device, the electronic device. The major advantages of this approach is that it is low cost and easy to manufacture. However, because of the low temperature growth process, zinc oxide nanostructure have high level of defects and also the process is quite slow. To mitigate these disadvantages, indirect integration approach has been tried. So in this approach, basically the nanostructures are grown at high temperature using CVD process, for example, which gives the material, high quality material at faster growth rate. Then these as grown nanostructures are transferred over flexible substrates using printing approach such as contact and transfer printing. The limitation of this process is that it is a bit expensive compared to direct, and it's also has more complexity because of printing steps. So with this motivation, here is the outline of my talk. I will present both direct and indirect integration techniques with device examples. So for direct integration, I will show the fabrication of piezoelectric nanogenerators over stretchable substrates. And for indirect integration approach, I will show zinc oxide nanosheet-based field effect transistor or flexible substrates. Finally, I will conclude my talk. So the present slide shows the in the direct integration technique by demonstrating the piezoelectric nanogenerator devices. So here is the process flow for such an approach. So first we take a rigid silicon substrate and we spin coat PMMA as a sacrificial layer. We spin coat PDMS to define the thickness of the substrate. We deposit a bottom electrode over it, then followed with the growth of a low temperature growth of zinc oxide nanowires on it. We encapsulate these nanowires in a polymer. Finally, a top electrode will be deposited to capacitive couple the generated charge in the nanowires, and the last step is to peel off all the device from the rigid substrate. The present slide shows the morphological and structural characterization of the active piezoelectric zinc oxide nanowires. As can be seen from this SEM image, the nanowire films is very uniform, and the XRD here showing the highly C-axis oriented film, which is needed for high performance of bank devices. In this slide, we can see the optical images of the fabricated devices. As you can see in this slide, that the device is quite conformal, very flexible, foldable, stretchable to a limited extent because of the rigid electrodes. And the SEM image is here showing the high infiltration of the perylene C, which is needed for high performance of bank devices. So in this slide, we show the characterization test bench for piezoelectric nanogenerators. So here is a mechanical shaker used to mechanically excite the device, and to record the signals, we have a Keithley current meter, electrometer, and then there is a resistive box to measure across different resistances. So in this graph, here in the middle, we can see the open circuit voltage at different pressure. And as you can see, when we increase the pressure, the output signal generated is increasing, and it can be seen that it can behave as a pressure sensor, showing the sensitivity of around 0.1 volt per kilopascal. We have also done the durability tests up to 40,000 cycle, where we can see that the signals are not degraded with the number of cycles. Here in this graph, the bottom, we can see the power output as a function of resistance. So we have measured at different frequencies. As you can see, with increasing frequency, we have increased the output power to around 0.6 microwatt, which is interesting to power low power electronics. Now, to show the potential of this approach, we have also fabricated large area devices. So to show that it's substrate independent fabrication approach, we have taken a typical bank cards. We have done the similar process as we've shown in the previous slides, and we fabricate a large area device of around 8 centimeters square. And then we have used shaker and hand excitation to see the power generated. And as we can see, with higher forces, using hand tapping, we can reach up to 35 microwatt of power, which is we have used to power portable electronics such as LCDs, which is not shown here, but we can successfully power them. So the next, we move on to the indirect integration technique, where we will fabricate zinc oxide nanosheet-based field effect transistors. So as we mentioned in indirect, first we need to grow zinc oxide nanostructures at high temperature. So here we are demonstrating another interesting material, another morphology, zinc oxide nanosheets rather than zinc oxide nanowires, which is normally used for fabricating flexible electronics. So to grow zinc oxide nanosheets, we have used R plane sapphire rather than C plane. So to exploit the epitaxial relationship. Here you can see in the SM image, we have obliquely aligned around approximately 30-degree aligned zinc oxide nanosheet uniformly grown over the substrate. And the XRD and Raman spectroscopy here confirmed the high crystalline quality of this nanosheet. The XRD also showing that there are highly epitaxial relation of this material with our plane, where we can only see on the plane correspond to zinc oxide 1, 1, minus 2, 0. So to transfer these nanosheets over flexible substrate, we have used contact printing approach. So it's kind of a roll printing. So here is a schematic showing the process. So what we have done, the as grown nanosheets, we have sandwiched them with the flexible substrates on it, and then this assembly is passed on to the roller, and the nanosheets are transferred over the flexible substrates. So we have used PET and Captain substrates to demonstrate this. So here is on the Captain, you can see the transfer images. So as you can see in the high magnification optical image, the nanosheets are transferred uniformly over the substrate. Then we have done typical lithography and lift-off steps to define the channel length. Here is the optical image after the device fabricated. Then what we have done, we have deposited the dielectric parallel C over it and the top gate electrodes. The final device is shown here in the slide, and we perform typical output and transfer scan to characterize the material and the device. So as you can see in the transfer scan in the middle, that the gate leakage for this device from parallel C is very low, which is very important. And the second is that negligible hysteresis is observed from these devices. The output scan showing the high ohmicity of the source drain contacts, which is needed to high performance. Here is the transfer scan done at different VDS, showing the enhancement of the on current, and we also tested the on current stability at higher stress values such as VDS 1 volt, VGS 5 volts, and ION was around 140 microamps, which remains stable for up to 12 hours of continuous operation. So to conclude, what we have shown in this work is that zinc oxide nanostructures can be used for printed electronics, for flexible electronics. And what we have demonstrated is two different approaches: direct and indirect integration of zinc oxide nanostructure for flexible electronics. In the direct integration approach, we have shown that zinc oxide nanowires can be grown at low temperature directly over flexible substrates. And here we have shown even on the stretchable substrates such as PDMS. Performance of these energy harvesters using direct integration approach is reached to 25 microwatt, which was used to power low power electronics such as LCDs. The indirect integration approach was demonstrated by first growing high temperature zinc oxide nanosheets, which shown high crystalline quality. And the demonstrated devices using indirect approach by contact printing them over flexible substrates also shown high performance in terms of high mobility of around 150, high on of current ratio of 10 to the power 5, and high on current. So with this, I would also like to acknowledge the funders for carrying out this work. So EPSRC, Hetero Print Program Grant, and also I would like to acknowledge my colleagues, previous and present labs, which helped me to carry out this work. Also, I would like to acknowledge the BEST group, which is headed by Professor Dahiya, And here are some links, important links which can be used to follow our group. And also, I would like to thank you for your attention. So now I would be very happy to answer if you have any doubt and questions. So thank you.